In this video, we'll go through an entire example of using the simplex method to solve a standard maximization problem. This question asks us to find the maximum value of the objective function f equals 2x plus 3y, subject to these constraints. We take a look at the constraints and recognize that they have the correct form for a standard maximization problem, therefore the simplex method does apply. And we're also told to assume that the variables x and y are non-negative. So that means x is greater than or equal to 0, and y is also greater than or equal to 0. And so sometimes those will be listed among the constraint equations. Other times we'll just be told to recognize that they're non-negative. And that's the other condition we need to know it's a standard maximization problem. Because it is, we can use the simplex method. So let's get started. The first thing we do is change each of our constraint inequalities into equations by adding slack variables, so that instead of x plus 2y being less than 10, we add a slack variable s to make that total equal 10. We do something similar by adding a different slack variable to the second inequality to get a left side that equals 7. And finally, we take the objective function and we rewrite it with everything on the same side of the equation that had the symbol representing the objective function, which means we move the 2x over to that side, we move the 3y over to that side, giving us negative 2x minus 3y plus f equals 0. So this is a complete system of equations now, which can be used to represent a simplex matrix, which is our starting point for applying the simplex method. The first thing we need to do from our simplex tableau is identify a pivot. So we look for the column that has the largest negative entry in the bottom row. In this case, that's the second column. And then we look at test ratios, which are obtained by taking entries in the last column and dividing them by the entries in the pivot column, although we never bother doing that with the bottom row, only with the rows that came from constraint inequalities. So let's begin. The first ratio we get is 10 divided by 2. The second ratio we get is 7 divided by 1. And we notice between those, 5 is the smallest of the test ratios. So now we know that our first row is the pivot row. And because we have first row, second column, the entry in the first row, second column is our pivot. Our first step with that pivot in this problem will be to make it into a 1. So we do that if we divide the entire first row by 2. That will change the 2 into a 1. And you can see that these other entries are exactly what we get, dividing 1 by 2, dividing 1 by 2, dividing 0 by 2, dividing 10 by 2, and so on. So the next thing we're going to want to do is make the other entries in the pivot column into zeros. To make this 1 into a 0, I can just subtract the first row from it. To make this negative 3 into a 0, I can add 3 times the first row, because adding 3 times the pivot to negative 3 will give me the 0 I want. So let's see what happens as we go through those steps. Let's begin with just modifying the second row. So I'm going to subtract the first row from the second row. 1 minus 1/2 gives me 1/2. 1 minus 1 gives me 0. 0 minus 1/2 gives me negative 1/2. 1 minus 0 gives me 1. 0 minus 0 gives me 0. And 7 minus 5 gives me 2. That's how I got my entire first row, my entire second row. And remember, the reason we subtracted the first row from the second row was entirely to make this entry a 0. Similarly, to make this entry a 0, I'm going to add 3 times the first row. So let's see how we get that. 3 times this entry is 3/2. If I add that to -2, the total is -1/2. 3 times 1 is 3. Add that to -3, I get 0. 3 times 1/2 is 3/2. Add that to 0, and I get 3/2. 3 times 0 is 0. Add that to 0, and I get 0. 3 times 0 is 0. Add that to 1, and I get 1. 3 times 5 is 15. Add that to 0, and I get 15. We've now completed a pivoting of the matrix, and we ask if we're done, and the way we know we're not done is because there's still a negative number in the bottom row, which means we have to go through an entire new round of pivoting, starting by finding a new pivot. So from this matrix, notice how we've removed the box that was around the old pivot, because that's no longer our pivot. We're finding a new pivot. And we can see that our new pivot column will be the first column, because that's the only column that has a negative number in the bottom row. Then we look at test ratios. We take the entry in the last column divided by the corresponding entry in the pivot column. 5 divided by 1/2 gives us 10. And 2 divided by 1/2 gives us 4. Between those two test ratios, 4 is the smallest one, which means the row that corresponds to that, the second row, is our pivot row. So we wanted first column, second row, and the 1/2 in that position is our new pivot. Now, in the previous run through the pivoting process, I took the step of making the pivot into a 1 first. But this time I'm going to illustrate that you don't have to do that first, and in this case it's easier if we don't. It'll actually be easier to see how to make the other entry 0 here if I don't change the pivot. Because I can take this 1/2 that's above the pivot and make it a 0 if I just subtract the pivot from it. And I can take this negative 1/2 in the bottom row and make it a 0 if I just add the pivot to it. So instead of making the pivot a 1 first, we're going to 0 out the entries above and below the pivot first. Let's begin by subtracting row 2 from row 1 in order to make that a 0. And afterwards, we'll add row 2 to row 3 to make that a 0. So going across, I'm subtracting 1/2 from 1/2 to get 0. Subtracting 0 from 1 to get 1. Subtracting negative 1/2 from positive 1/2. So 1/2 minus negative 1/2 is the same as 1/2 plus 1/2. That's how we get 1. 0 minus 1 is negative 1. 0 minus 0 is 0. And 5 minus 2 is 3. Now the second row stays as it is. We're not changing the pivot row yet. We're going to move on to changing the third row. So I'm changing the third row, making this entry into a 0. And to do that, I'm going to add row 2 to that row. That way I get the 0 from adding the pivot to what's already there. So 1/2 plus negative 1/2 is 0. 0 plus 0 is 0. Negative 1/2 plus 3/2 is 2/2. That's just 1. 1 plus 0 is 1. 0 plus 1 is 1. And 2 plus 15 is 17. Finally, we could change this pivot into a 1, but we can see there's not really going to be much need to do that, because after this round of pivoting, we don't have any zeros left in the bottom row. So there probably is not going to be a need to change that into a 1. One of the reasons we change pivots into a 1 is to make it easier to recognize how to make zeros by adding and subtracting multiples of the pivot row. But we're not going to have to do any more of that because there are no negative numbers in the bottom row. We're going to be done pivoting the matrix. So there's no longer any value in trying to make that entry in the pivot position into a 1. So let's just skip that step now. Moving on, we're going to read our answer for the standard maximization problem from the final matrix we obtained after pivoting. So first of all, we identify the active variables, which are the variables that have only one non-zero number in their column. Each of these columns have only one number that's not 0. So each of those columns are active columns. X, Y, and F are active variables. The other two columns, corresponding to the variables S and T, have multiple non-zero entries, so those are inactive variables. Remember that inactive variables are automatically equal to 0 in our final answer. Then we can use that in the equations we get from looking at the various rows of the matrix to obtain the values for the active variables. This first row of the matrix corresponds to the equation y plus s minus t equals 3. And then if we plug in the values s equals 0 and t equals 0, we see that y is equal to 3. If we do the same thing with the equation obtained from the second row of this matrix and plug in the values of the inactive variables, we end up with the equation 1/2 x equals 2, which simplifies to x equals 4. And then finally, the last row of the matrix represents the equation s plus t plus f equals 17, and plugging in zeros for the inactive variables tells us f is 17. That means the maximum value we can get from this objective function is 17. And the way to get that maximum value is by plugging in values for the variables x equals 4, y equals 3.